Welcome to the Toronto Vision Seminar. It's my pleasure today to introduce today's speaker, Andrew Owens. Andrew is an associate professor of computer science at Cornell Tech. Before that, he worked as an assistant professor at the University of Michigan, and he did his PhD at MIT with Bill Freeman and Antonio Torralba, followed by a postdoc at Berkeley with Alyosha Efros and Jatinder Malik. His research has a few different thrusts. He works on self-supervised learning from video and controllable video generation, multimodal learning, developing models that learn about the world by finding structure in sensory signals like sound and touch, image forensics, developing better models for detecting fake images, and finally, most recently, his group has done work on using diffusion models to generate visual illusions. Andrew has been recognized with a Sloan Research Fellowship, an NSF Career Award, and his work has been honored with Best Paper Awards at WACV, CVPR, and RAL. Before we get started, I'd also like to thank our sponsors, the Faculty of Arts and Sciences, Google DeepMind, and the Fields Institute for making the seminar series possible. And also Jasmine will be going around and taking pictures, if that's okay with everyone. So please join me in welcoming Andrew Owens.
Oh. Thank you for the really kind introduction. It's been great to be here and get to see all the really exciting research going on here. Okay, so consider this painting by Salvador Dali. You might not notice it at first, but there's a hidden face in it that appears when you rotate it. And, making images like this is really difficult because every visual element in the image has to have multiple interpretations. For example, this lip also has to be a person. And this guy's wondering, if artists can make illusions like this, can we kind of get generative models to do it too? We've seen these models do really impressive things. They can make videos, they can make really compelling art, images. Is this something they can do as well? And we thought it'd be interesting because it also requires you to deal with these sort of ambiguous stimuli that humans seem to interpret in this specific way. So this is work that was led by my former PhD student, Daniel Gang, and former master's student, Aaron Park. And you want to just start by looking at off-the-shelf diffusion models. With diffusion models, you start with random noise, and you just iteratively denoise until you end up with a clean image. And at each step, what you're doing is you're taking your noisy image, you're passing it along with a text prompt into a diffusion model, and the diffusion model is estimating the noise. Now, what if we take the same noisy image, apply a transformation to it, like flipping it upside down, and then pass that into the diffusion model with a different text prompt? This would give us noise that if we use for denoising, would denoise the upside down image. Then we could invert that transformation, average the two noise vectors together, and get a composite noise that tells us how to denoise both of these views at once. And so, just like in regular diffusion, we'll apply denoising iteratively, but in this case, we'll use this composite noise estimate over and over again. And we found that doing this actually let us generate some really interesting results. So here's an example. From one perspective, this is like an oil painting of people around a campfire. But if you rotate it, you see an oil painting of an old man. Here's another one. It looks like a giraffe. Can anybody guess what it'll look like if we flip it upside down? Yeah. You kind of see the beak in a penguin. It's like an oil painting of a snowy mountain village. Rotate it 90 degrees. You get a horse. And we also got thinking like these rotations need to work. What if we try something a little bit crazier? What if we rotate the center of the image? Albert Einstein converts into Marilyn Monroe. Okay, so that worked pretty well. What if instead of rotating that center 180 degrees, we use 135 degrees? Seems like a very simple change. We'll take our PyTorch code, we'll replace 180 with 135, and we'll run the same procedure again. And this is the result you get. And it's not so great. So, why does it seem to completely fail when you go from 180 to 135? Well, let's look at what's going on here. When you have a diffusion model, you're passing in a noisy image. And in this case, instead of passing in the noisy image, we're passing in a transformed version of the noisy image. And this is an issue because the diffusion model is assuming your input has certain properties. namely that you're getting a noisy image that's a weighted sum of some signal and noise. And secondly, that the noise is IID standard Gaussian. And there's no guarantee that when you transform your noisy image that you still have these properties. And that's why this didn't seem to work, because implicitly, when we were doing the rotation, we were performing bilinear sampling. And even though that seems like a very safe operation, we're changing the variance of the noise. And when we take the weighted sum over the pixels, and as a result, this kind of it gives us something sort of out of distribution for the diffusion model. So the natural question then is, what transformations do work? If rotation by 90 degrees can work, what's the set of transformations that we can apply here? Well, if we kind of think about the properties we need to have, weighted sum of signal and noise needs to be IID Gaussian. To satisfy this first condition, we can use a linear transformation. So we'll just set V to be some matrix multiplication. And by kind of linearity, it'll have this property. We can kind of distribute A, and we're left with a weighted sum of a transformed signal plus transformed noise. Now, the second condition says that this transformed noise still has to be standard IID Gaussian. So we're going to have to make sure that transformation preserves that second property as well, that this transform noise is standard IID Gaussian. And in order to satisfy that, we can have A be an orthogonal matrix. If A is orthogonal, then we'll get out another standard IID Gaussian after applying this transformation. And this raises another question, like, what are the orthogonal transformations of images? Like, what does that leave us with? If you apply some arbitrary orthogonal transformation to an image, it won't be very meaningful. You'll just get something crazy will happen. But there's one really important special case that we've sort of been implicitly relying on, which are permutation matrices. If you're permuting the pixels, that's an orthogonal transformation. So this means that, and with the permutation is kind of shuffling the pixels around. So this suggests that our method is a way of essentially creating visual anagrams, or images that change their appearance when you rearrange their pixels. And that's why this 180-degree rotation works. You're kind of permuting the pixels when you do that. It's also why 90-degree rotations worked. And even that the inner circle looked really complicated. If it's a 90-degree rotation, then it should still be an orthogonal transformation. But this sort of gets thinking, like, okay, what are the other interesting things we do with orthogonal transformations? Well, how about a kind of taking an image, breaking it up into little blocks, and moving those blocks around using little hinges. So this looks like a young woman, and then it looks like an old woman. We can also kind of generalize this. We can create we call polymorphic jigsaw puzzles. We can make a jigsaw puzzle where if you rearrange the pieces, you get something else. So this is the result of arranging a jigsaw puzzle in one configuration. It looks like a kitten, but then if we shuffle the pieces around, reassemble it, we get a puppy. Here's another example. It looks like a watercolor to color of a rabbit. We'll reassemble the pieces and get a duck. And my student Daniel got really excited about this, and he printed a whole bunch of these real jigsaw puzzles, so you can actually do it in person. I have a couple of these in my backpack if anybody wants to play around with them. You can actually just create these real physical jigsaw puzzles. It's actually not that fun in my because you can sometimes create like half dog, half cat, and they won't fit together. It's a little bit of a challenging jigsaw puzzle, but it's definitely something we've had a lot of fun with. You can also generalize it. Instead of having these jigsaw puzzle pieces, you can just permute the patches in an image. Example is the kangaroo, permute the patches, and get a lemur. Okay, but what about 3D transformation? So here's a really famous example you might have seen in a vision class before. This is a painting by Hans Holbein, and you might not notice it at first, but there's this hidden skull here. And it doesn't look like that until you look at it from a particular angle. If you view this painting one particular angle, you'll see a skull. And so these general 3D transformations are really complicated, but we can approximate this one using a skew. And that lets us create images like this that are kind of inspired by the painting. It looks like a portrait. And then if you view it from just the right angle, you should get a skull. And we're trying to think of like other transformations that aren't permutations but are orthogonal. And the only one we came up with was what I think is really interesting is inversions. So if you assume that your pixels range from -1 to 1, if you just negate them, black becomes white, white becomes black, then that's an orthogonal transformation, and this should satisfy the properties you need. So here's one example. It should look like a landscape. And now if I invert the color, white becomes black, black becomes white, I should get houseplants. Which is an illusion I haven't really seen before. So it was fun to, along with the puzzles, it was fun to like find new kind of interesting things we could do with this. And one thing that I like about this, as someone who started in computer vision a long time ago, right, before deep learning, when we were working with edge-based features, these two images, they're negations of each other, and they have exactly the same edge magnitudes. If you were to kind of run an edge detector on it, you'd have edges in the same places, but they have completely different interpretations. So it suggests that edges, as you might imagine, edges aren't really everything, or at least the contrast is very important in those edges. You might ask, can you generalize this to more than 2 views? We're able to make some 3-view illusions too. It was a lot harder. We had to cherry pick these because it was very failure prone. But this is one example. Should look like oil painting of houseplants from this perspective. Now, if we rotate it, should get Elvis. In case people don't see it, I'll just kind of highlight it. It's kind of subtle. And then if we rotate it again, we get Einstein. Okay, so there's a lot of really, there's one really important implementation detail that I've left out so far, which is that this is a pixel diffusion model. So most of the models today we use are latent diffusion. They operate in some learned latent space. This is all done with pixel diffusion. And it's really important because if you consider a latent diffusion model, the latents essentially encode patches of images. And if you permute the latents, what you're doing is you're kind of permuting patches, but you're not actually changing the orientation of the things those patches encode. The patches are permuted, but not the content of the patches. And so it's kind of what happens when you use a latent diffusion model for this is you're essentially moving the patches around, but the underlying content isn't moving with it. And so if you try using a latent diffusion model, you get results like this that have these sort of artifacts that look similar to what you'd get if you were to kind of permute patches of an image without changing their contents. And there's also 2 really closely related works that I'd like to point out. The first is a Colab notebook, actually, by Matt Tansik that was sort of floating around we learned about. And it kind of introduced the idea of denoising multiple views to make illusions. And I guess they just did this rotation illusion, but they used a latent diffusion model. So you end up having some of these artifacts. And you have these 4 illusions that use approaches that are really similar to what we did. The other is this really nice work by Ryan Burgert and others called Diffusion Illusions that was at SIGGRAPH recently. And they use a different approach. They use score distillation sampling. They create images and that they optimize these illusions using optimization and specifically using score distillation sampling. And they can do some really interesting things with this. They can create illusions like this that are or these overlay illusions that that you couldn't do with our method due to permutation. More recently, this year at CEPR, there's really interesting work by Pascal Chong and others that had several different contributions. One, which is they found a way to actually make latent diffusion work with these models. Specifically, they can kind of like decode the latents into clean images, do operations in clean image space, re-encode the images, do some error correction to deal with what's missing, and then repeat. And they're able to actually use latent diffusion for similar kinds of illusions. And they're also able to see some really interesting techniques from computer graphics and kind of rasterization, and the model can kind of create these 3D illusions that are kind of they're posing the problem as kind of a texture mapping. So you can kind of create these like hidden images that get revealed when you place a cylinder on a scene. Okay, you might ask like what prompts work here? Well, one that works really consistently is following oil painting of people on a campfire, oil painting of people an old man. We saw this work really consistently, and here's a bunch of samples from those prompts. You can see they're all pretty consistently working well. And why is that? Well, if you think about it, the prompts are kind of leading us to a good result. For one thing, we have this description of an oil painting. And if you think about it, oil painting is this kind of abstract thing, and it gives you a little bit more flexibility to like reuse visual elements between the views. There's also this other thing, old man. And this works because people are really sensitive to faces. Like there's even this phenomenon called pareidolia, where you see faces even when there aren't faces. Like you might see them on the moon or a bag of chips or something. And you can kind of get humans to think that there's a face in an image relatively easily. On the other hand, if we instead of using painting, we said photo, that's not going to work as well because the photo is very constraining. And then if you pair it with a prompt like the Queen of England, that's going to be even harder since it's a really visually distinctive thing that we're making. And so you end up with results like this, which, this maybe sort of work, but, maybe there's also some kind of issues there. And I was going to kind of point out one of the reasons why this works is because you think about the fact that our model's learning a score function. When you train a diffusion model, the denoiser, you can kind of think of as a score function. And what we're essentially doing is taking advantage of the fact that when you learn a score function for noisy images, you also get a whole bunch of other score functions for free. You get the score function for the flip version of the image, rotated, permuted in general. It's like just by learning this one thing, you get this whole bunch of other things. And if you wonder, like, we're averaging together these noise vectors, why is that valid? Like, can you do that? Well, what's happening then is you're essentially adding together these two score functions. And what you're essentially doing is you're approximately sampling from a product of experts. So you're getting images that we're following the score function and we're sampling images that are kind of likely under both distributions, distribution of ordinary images and the distribution of flipped images. And so by adding those noise together, we're essentially sampling from this other distribution. And this is a line of work that a lot of people have looked at in sort of compositional generation. They've looked at different ways that you can look at analyze these models and do different types of compositional generation with them. That said, there's still a lot of issues. One is the composition ability sometimes fails. Like you might ask for a monkey and some fruit and end up with them just being two separate things in the same image. Also, the success depends a lot on the prompts. We saw that photos, the early work as well. And finally, there's this assumption that you can create illusions using orthogonal views. And unfortunately, this doesn't always work. There's a lot of really interesting illusions you might want to make that you can't express using orthogonal views. And one that we really wanted to do was what's called a hybrid image. So if people seen hybrid images before, so here's one really early example of this from this painter named Charles and Alan Gilbert. If you look up close, you see a woman staring at herself in a vanity. What do people in the back see? Sometimes this works. What was that? A skull, yeah. So if you stand from far away, or if you reduce the size of the image, you'll see this hidden skull. It's kind of a memento mori. And let us see if we can make these, but we couldn't figure out how to do this as a permutation of the pixel. There's no permutation that'll give you like a small version of the image that we could think of. So let's think of it, and I should say this is something that Oda Oliva at MIT has had a really nice line of work creating these solutions for. So let's look a little bit about why this illusion works. Here's what's happening. When you see an image, if you're up close, you see all the details. You see like every petal on these sunflowers. If you see it from far away, like one of these sunflowers in the back, you essentially see like only the low frequencies. You're only seeing like a blurry sunflower. You're not seeing every detail. And so if we were able to kind of decompose what you see at different distances, you'd see the high frequencies only when you're up close. In the middle, you see mid frequencies. If you're far away, you just see the low frequencies. And one thing you might notice here is just like an interesting mathematical structure. Like what you see at different distances corresponds to linear functions of the image. Like you could express the low frequencies as a linear transformation of the image, or the high frequencies as a linear transformation. So if we were able to make image generation methods that allowed us to control individual linear factors of an image, then we'd be able to make hybrid images. We could create images that have different prompts for different factors. And this is work that was, again, led by the same group of people, Daniel Gang and Aaron Park. I want to see if we can create other illusions where we can control these linear factors. And we call this approach factorized diffusion. The approach is very similar to the approach we've already seen. During each step of the reverse diffusion process, we'll take our noisy image and we'll estimate noise using two different prompts. Then we'll apply our linear decomposition to the noise estimates. Then we'll reassemble the noise, taking one component from each of the prompts, giving us a composite noise estimate. And we'll take that composite noise estimate. It's got its low frequencies from one image, high frequencies from another. With low frequencies from one prompt, high frequencies from another prompt, and we'll denoise using that prompt. And you kind of might ask why this is sort of valid and why it works. Well, it turns out that this is why are we like low pass filtering the noise? It seems weird at first glance. What's happening is this reverse diffusion step, this update that we're performing is linear or nearly linear for both of its arguments. So when you do an update to get the one step of the reverse diffusion process, and you use a schedule like DDIM, you're doing an update that's linear in both of these two different arguments. And if you kind of exploit this fact, you can show that the update that we're doing is equivalent to doing an update just for the image's different components independently. So we're updating each component of our noisy image with the corresponding component, the prompt for each of its corresponding components. So we're doing kind of like a component-wise update. Okay, so this approach lets us kind of separately control the low and high frequencies of the image. And you can kind of define the two different transformations as a Gaussian filter for the low frequencies and residual for the high frequencies. Like I can kind of rewrite my input X as the sum of a low pass filter here plus a residuals, the image minus the low pass. And those will be my two different views. Like I'll use those in my decomposition. And this is an idea that Oda Oliva has used to create hybrid images, but they do it sort of manually. So she was able to create these really interesting hybrid images by like kind of manually taking two images that are kind of similar structurally to each other And you could make images like this, where it looks like Albert Einstein up close, and then from far away, Marilyn Monroe. But it's a kind of manual process. You have to be really careful to find two photos that are like really well aligned, and because otherwise you won't really group them together. And so, but whereas our approach is to let us generate images that are hybrid images using two different text prompts. And so here's one example. What do people in the front see?
Okay.
Okay. Anyone in the back? Something different? Yeah, yeah. What was it? Yeah, yeah. So you took off your glasses, which is a great way to do this. Okay. So if I smaller. So the two prompts were lithograph of flowers and lithograph of panda. All right, here's another one. Do people up front see? Okay, I heard waterfall. How about in the back? Anyone see something different? Yeah, yeah. It looks like, I think it's the problem is actually pig. It does look a lot like a cow. Yeah, so those are the two different prompts. All right, here's another one. Okay, up front, flowers, I think. How about in the back? Yeah, so it was Marilyn Monroe. So you're inspired by Odaliva. And you might ask again, can we do three? Can we have three different prompts and have an image where you view it from many different directions, many different distances, you get something else? Again, we had to really cherry pick these, it's a little error, but we did find a couple where we could get it to work. So this is one where up front, this one doesn't always work, depends on the room, how far people are. What do people up front see? Waterfall, okay. How about people in the back? I heard skull, okay. Okay, so waterfall, skull. And now, can anybody see something else even more distant? Yeah, yeah, exactly, yeah. So yeah, we were able to create a couple of these, yeah. Okay, so that's one decomposition we do. We also asked like what other decompositions there are. Well, it turns out there's a lot of like natural linear decompositions you get in the wild. So one example is color. If I at night, if I see this image, it'll look like this because I don't really have color vision at night. During the day, I'll see this. And you can think of this as being another linear decomposition. One of the components converts the image into grayscale. It could kind of crudely do that by averaging the three channels together. And then what's missing from that is the color. And we can have the second component just be the difference between the original image and the grayscale version of the image. And this lets us create images where if you were to see them in grayscale, you'd see one thing. If you were to see them in color, see another. You could demonstrate this by we've tried like printing them out and like turning off the light. And this will sometimes let you then see the hidden grayscale image. But given constraints here, I'll just show an image and it's going to be in grayscale. What do people see? Flowers, hopefully, yeah. Okay, how about any guess what it might be in color? Yeah, exactly. It'll be a teddy bear. Yeah, good call. Yeah. Okay. So here's another one. This landscape. This one I think you can kind of figure out what's going to be. Anybody guess what would be a color? Yeah, it'll be a tiger. Yeah. So yeah, you can kind of it's gonna make sense, right? If you color that in orange, it'll suddenly look like a tiger. Another application we came up with was simulated motion blur. So if you move really fast while you're taking a photo, it's akin to convolving the image with an oriented blur kernel. And so I can kind of simulate what an image would look like when it's rapidly moved. And I'm going to just show you, it's obviously like simulated motion. You have to move it very fast in order to achieve this amount of blur. But we again can use these two different, the original image and the blurred version as, we use the blurred version of the image and the difference between the image and the blurred version as our two different components. Let's make images like this that should look like a duck. And then if I shake it really rapidly, really, this is just kind of an animation, but if I were moving it really, really rapidly, I would see a rabbit. Which again, it's just an image where if you kind of blur it, you get in a certain oriented blur. So we get beehive, and then if I blur it, get a dog. One thing we can also do is, all the examples I've shown so far, we're generating something from two different prompts. We can also freeze one of the components and just generate the other. So for example, we can force the low pass we generate to match this image of Thomas Edison, and just then generate a new high pass using a prompt like photo of a light bulb. And this is really closely related to work in inverse problems. So there's a lot of work on solving inverse problems and doing this using diffusion models. And our approach, if you do everything this way, is exactly the same as this very nice work by Choi and others called ILVR, which used in inverse models not for creating illusions, but instead for image editing. And mathematically, it's actually equivalent to this method. So it lets us make images like this, or up close, you see a light bulb. Far away, you see Thomas Edison. Here's another one. Do people up front see? There. Okay, what do people in the back see? Wait. So you should see David. Yeah. So yeah, you can just go to somebody's website, download the picture of the face, and then the polar bear works really well for like pretty high success rate for some reason. I don't really know why, but that's always a good one. Okay, so you can also add hidden messages to images. You can take a photo, add some text to it, and then make that be the low pass, and then fill in the high pass. So for example, here, this should look like the Duomo in Milan, and then if you see it far away, you'll see the message says ECCV. This one on the right should say should look like the Seattle skyline, and there's a hidden message that says CVPR if you stand far away. And the reason we made these was we were really, really lucky. We actually used that last one as part of the official CVPR T-shirt. We were really surprised. We were talking about it earlier. We were really surprised that the CVPR general chairs asked us if we could make an illusion for the T-shirt, and we tried a whole bunch of things, and this is what we came up with. So if you kind of went to CVPR, you might have picked up this T-shirt, and we also did a little bit of manual editing on it because just to make it aesthetically better. So the result I showed before is the generation, but here we touched it up a little so that but not the illusion part of it, just to make the mountain look better. And yeah, then if you were kind of saw your friend as they're going down the escalator, hopefully it would reveal this hidden message. I don't know if this actually worked that often. We were hoping people would just see the hidden message as people walked around. Okay, so all these illusions so far have involved images. My group works a lot on audio, and so we're wondering, it's possible to make illusions using other modalities like audio. And indeed, we found that we can. So this is one illusion. At first glance, it should just look like an image of a bunch of corgis, but there's actually a hidden signal here. Let's treat this image as an audio spectrogram. The x-axis will be time, y-axis is the energy, is the frequency, and the intensity gives you the energy. And when we convert it into a waveform, this is the sound that we hear. And this is work that was led by my former PhD student Ziyang Chen, and also collaboration with Daniel. And we want to see if we can make images like this that have these two different uses. Call them images that sound. Inspired by some of the other previous work with similar titles in the like objects that sound in the audiovisual community.
All right, so where do you get the phase?
Oh, where do we get the phase? Yeah, so right there we're using a neural vocoder, but you can also just use Griffin-Lim to estimate the phase, and we got pretty similar results. So yeah, spectrogram only gives you the magnitude. there's a whole bunch of ways to estimate phase, and yeah, we found it was pretty similar. Yeah. Other questions? Okay, great. So we wanted to make these solutions. One of the reasons we were interested is wanted to see if you could find examples that are kind of at the intersection of these two different modalities. Like, can we find examples that are like in the intersection of natural images and natural spectrograms for audio? And artists have like done something a little bit like this. You might have seen like some artists, some musicians will add hidden images in the spectrograms for their songs. Like I think one famous example is there's an Aphex Twin song, and it has this like a hidden face in it. I can play the sound. It's maybe not so natural. Like it's hard to say. It's a very dissonant. You could argue maybe the audio is a bit unnatural. There's lots of other people hid pictures of their cats. There's famous examples from other artists. And we're wondering if you could find examples that kind of lie at the intersection of both of these distributions. Things that would be valid images and something that would be valid sounds. And so the way we can pose this is sampling from a product of experts where the visual and audio modalities are the two different distributions for video, for images, distribution for audio are the two different experts. And we can apply very similar techniques we've seen before. We'll start with some noise, in this case, latent in a latent space, and we'll apply a image diffusion model with one prompt, and then we'll take the same latents and we'll also plug it into an audio diffusion model, giving us a noise estimate for audio. And one really key thing is that these both have the same latent space. And there are audio and diffusion models that have the same latent spaces as image models, which just allows us to do this. And then we'll just take a weighted average of these two different noise vectors. It's going to be a weighted average that varies over time. We found that one of the two modalities will dominate if you the images will often dominate if you do like kind of an even average. So we have like a schedule where we allow the audio model to get a little bit of a head start before we do a complete average between them. And we'll just take that composite noise estimate, weighted average of the two latent noises, and then we'll just, so like before, do iterative denoising, and finally end up with a clean latent. Then you can take those latents, generate a clean spectrogram, and then, like we were saying before, you can convert that into a waveform using a vocoder. This could be a neural vocoder. It can also be a classical technique that like iteratively solves for the phase, and then you can get a waveform. So here's some other results. I'll show a couple of samples from these prompts. Painting of cute dogs and dog barking are the two prompts. And you can see like there's something weird. Like you can look at these images, like something funny about the dog's legs. And indeed, you see like each one's an onset for the barking sound. Here's another sample from that prompt. You see like each leg. And you could also make examples of this, like a pond of water lilies, and the sound could be frog croaking. It doesn't actually have to be like any relation between these two prompts. Okay, so one thing I'm like, why study illusions? Why work on this? Well, it all started as really curiosity-driven research. But I also think there's a lot you can learn from studying visual illusions. For one thing, illusions can help you get a better sense for how well human and machine perception is aligned. For example, I think it's really intriguing that diffusion models and humans seem to both kind of have the same interpretation of this, to some extent, of this ambiguous stimuli. Like they both see a landscape, and when you negate it, they both perceive potted plants. And there's been some really recent work in this direction, like predated ours, and recently by Janie and Garros and others at Google that have done some really interesting work where they've plugged classic visual illusions into diffusion models and asked them to interpret it. For example, recently they have this work where you can take an image like this classic illusion, and ask a video generator to predict the future in the video, and it sees just like we see a Dalmatian, and the model seemingly sees one as well. I think there's also this long tradition in vision science of using illusions to understand how human visual perception works. And I think it's interesting that a couple of studies in psychology recently have used these illusions as stimuli. For example, very recently, Boger and Firestone have used these visual anagrams as part of stimuli in a study, because they arguably have like the same texture and curvature, and so you can use them to kind of measure how people perform different discrimination tasks, and see how they perceive them differently, because you're giving them two stimuli that are like the same size, or that have the same number of gray pixels, and they can control for a number of factors and see how they change their interpretation. I think it's also useful for looking at machine learning ideas like composition. We're kind of creating these we're using composition to create images that have two interpretations. And also, at the end of the day, I think probably the best use of these is also just for entertainment. And we've had a lot of fun doing that. And one of the best applications of this, we actually found out via email. So my PhD student, Daniel Gang, got an email from this PhD student. And in his email, he said, believe it or not, I used your code to help propose to my girlfriend successfully. And he made this puzzle hunt as part of his proposal. And as part of the proposal, he made these visual anagrams. And you had to figure out how to kind of unscramble them to reveal hidden images, which gave the next clue for the next puzzle. And I'm glad to report they're happily engaged now. Okay, so we talked about ways you can kind of push these image diffusion models to do what I think are kind of unexpected things, zero shot, without any additional training, just through clever prompting. But large video diffusion models have also been appearing in recent years. We saw before, there's like really cool things you can do with this. So I was wondering, it's possible to pull out latent abilities out of these video diffusion models, just like we've been doing for image models. And my group's been working a lot on tracking. And if you think about it, tracking is really closely related to video generation. With video generation, you're kind of generating videos that should be really trackable. Objects should persist between frames. They should be able to persist through occlusion, deformation, changes in lighting. And so internally, the models must have some capability to do some tracking or have some mechanisms that are doing tracking-like things. And so we wanted to see if it's possible to kind of extract these abilities from diffusion models. Is it possible to use diffusion models to exploit the fact that they're able to create these videos where if you run a tracker on them, you get results? We could have take advantage of that to perform tracking as well. Tracking, in other words, emerge as part of these video diffusion models. And so it's a new idea. There's been two really interesting recent lines of work that addressed it. The first is methods like DIFT that kind of treat diffusion as its representation learner, where you can kind of pull out some image features from an image generator and use them for matching using nearest neighbor. And what's really cool about this is all zero shot. You don't have to train anything. You just take an off-the-shelf model, you grab some features. But unfortunately, it's very architecture dependent. You need to find the right features. It doesn't necessarily generalize between architectures without some work. And this was other really interesting line of work from Dan Yamen's group at Stanford where they're called counterfactual world modeling, where they train a masked autoencoder to produce future frames of video. Then at test time, they'll predict the future, and then they'll then they'll do it a second time, where they mark a dot in the initial image, and they'll predict the future, and then the future will have the dot in it, and you can subtract that the image that the future that has the dot from the image without the dot, and figure out where the dot is. And this is a really appealing idea because it's all based on prompting. But unfortunately, you have to prompt this like special purpose model. Like you had to train a model just to perform the task, this kind of future prediction masked autoencoder. But this guy's wondering, maybe we can create, we can do a similar approach with just off-the-shelf video diffusion models, which kind of give us the best of both worlds. And this is work that was led by my PhD student Ayush Srivastava and master student Sanya Mehta, and also collaboration with Daniel Gang. And here's what we want to do. We'll take a video and we'll mark an image conditioned video generator, and we'll kind of just take a video, and then we'll take the initial frame of the video and we'll just draw a red dot on a point that we want to track. And then, if you kind of zoom in, you can see there's like this little red dot there. And then we'll propagate that red dot throughout the video using SD-edit. So we'll add some noise to the subsequent frames of the video, and then we'll ask the model to denoise the video. And this is the result we get. It'll propagate that dot to the future, but there's going to be some errors. Like you can sort of see the dot here, but you can also see it sort of disappears sometimes. So it's a good start, but not perfect. So the issue is, I think that the model hasn't seen a lot of these dots, and it knows there's not a dot there. Like it sees later frames of the video that have no dot, so it maybe concludes it doesn't really need to put the dot there. So we found a trick we can use to address this. We'll kind of enhance the signal we're putting in using negative prompting. So we'll use a video diffusion model to estimate noise using an image that, again, has had a red dot marked on it. But then we'll use as a negative prompt the noise from the original video. So we'll denoise using both this edited frame and one with no edits. They'll give us two different noise estimates, and we'll treat the noise from the unedited frame as a negative prompt. We'll add the two noise vectors together, but we'll sort of emphasize the one with the edit and ignore the one without. And think of this kind of sampling from a distribution that's sort of like we think of all the possible futures that would come, all the possible generations that would come from this model. We'll kind of prioritize the ones that have the dot and deprioritize the ones that don't. This seems to work much better. And one other trick, you also have to rebalance the images. If you don't remove the red in the original video, it'll get distracted. But if you can see here, you can generate these videos that follow that person much more closely. And now we can just read off the location of the track using a really simple, like the world's simplest point tracker. Like just like find use template matching just to find the red dot in the images, and then kind of interpolate if you don't find it. Really slow though. Each dot takes like a half hour to generate one of these videos on one GPU. So it's not the most practical tracker, but it's all 0 shots, and we can end up generating images that have these red dots and then extract their locations to do tracking. There's one other trick. When you regenerate the video, there'll be a lot of artifacts. Like you see there's something messed up about this horse's feet and its head. And so we can do kind of like course define approach. We can generate our video, and then we can figure out where the dot is and then regenerate it. Only the second time we regenerate it, we'll do in-painting. Sorry about that. The in-painting will be, so we'll regenerate the video, but we'll only generate this small region centered on our estimate of the location of the dot. So this will let us freeze everything else and get a better video generation that more closely matches the original. And with all these tricks together, we get actually a pretty good tracker. So here's some of the raw outputs just to the generated videos. You can see it's pretty good at dealing with occlusion, which is something that video generators are really good at. It has to deal with occlusion, so handles it pretty well. Another case here, this car drives by, it still drives the red dots, and you can kind of expensively put this together to get tracks for the whole video. And quantitatively, still far from supervised tracking, but interestingly, it seems to be quite competitive with other self-supervised tracking, though maybe not as good as like the very best approaches, like ones where you train a separate self-supervised model. But compared to other 0-shot methods, ours does quite a bit better. And if you give our model like high-res video, which is sort of cheating, if you give it like the full res, we get a big boost because the video model is trained on much higher resolution than what these things are normally tested on. And it seems to work across different video models. It seems to be the case that better video generators do better. There's kind of a trend toward that, though kind of a weak one. And we found it's really important to do that counterfactual tracking. But of course, it doesn't always work. Sometimes it misinterprets what we want the dot to be. I think it's like a lens flare or just a red on the screen. It also sometimes has like a 3D interpretation of the dot, which is sometimes funny, and so it loses it. And also there's this funny case where it will due to symmetry, it'll add other dots. Like you put a dot on one leg, and it's like, okay, there's probably a dot on the other leg too. All right, I want to thank all of my collaborators, especially Daniel Gang, Aaron Park, Seong Chen, Yusuf Stava, and Sonia Mehta, and also thank all of you. Thanks.